remember we proved that the extremal number of a cycle is of length 2k is at most like a constant times n to the 1 plus 1 over k. So in the case here, k, if 2k is 4, we've got n to the 3 halves here, right? We also proved that a complete bipartite graph with parts of size k is at most, what was it? n to the 2 minus 1 over k. And actually, k22 is just C4, right? So sort of in two different ways, we've proved that the extremal number is at most n to the 3 halves, because here, if k is 2, we get 3 halves again. But remember, so what we did last time was some kind of a supersaturation result for triangles, right? Where it was like, we imagine we have a graph with way more edges than the extremal number, and we want to know how many copies of the graph does it have. And today what we're going to do is something in that kind of that type of flavor for the graph C4, so for the 4 cycle. Okay, so last time we did triangles, and this time we're doing quadrangles or squares. I mean, that's what C4 looks like, right? It looks like a square. But actually we're gonna actually deal with when the number of edges is way bigger than the extremal number. So if the number of edges in a graph is, let's say, for example, half the number of total edges, then okay, if n is large enough, which doesn't have to be very large, then the number of edges in G is going to be a lot bigger than the extremal number for C4, because as we said above, the extremal number only grows at a much slower rate. The extremal number grows at a rate of at most n to the 3 halves, whereas here we're dealing with quadratic number of edges, so it's like kind of n squared over 4 or something. So obviously then, because the extremal number of C4 is, or the number of edges is bigger than the extremal number, you have to have some C4s in the graph. So G has some C4s. I always find it awkward to pluralize mathematical notation. So it's not C4S, but C4s. Some people write an apostrophe or something, but that feels wrong grammatically as well, right? I'm not doing possessive or something, but anyway, C4s. So how many must it have is basically the kind of question we're going to address. Any questions about that? So there is a bit of a subtle thing here when we're dealing with, so last time we were dealing with triangles, and it's kind of easy to say what is a copy of a triangle. There's a subtle thing about C4s in the sense that, I don't know, I mean, well, yeah, so how do we kind of measure the number of C4s or 4 cycles in a graph G? I mean, in particular, how many 4 cycles does a 4 cycle have, right? And it kind of, if you think about it, this kind of has different answers depending on what you mean by like a copy of a 4 cycle, right? Because in some sense, you would say that a 4 cycle has only one copy of a 4 cycle, just itself, right? This is just one 4 cycle. It kind of has only one 4 cycle. But if you count copies in a sort of, I don't know, labeled copies or something like that, like imagine well, if you count, with like different kinds of symmetries, you might come up with 8, right? Because if you think about, I don't know, how many ways or how many 4 cycles does this have? You can kind of think of it as like, I could label the 4 cycle, I could do 1, 2, 3, 4. If I wanted to count a copy as a way of picking, say, 4 vertices that are joined in a cyclic way, you could kind of think of it as counting 8 different copies, if that makes any sense. That's a good point, but that's not how we counted triangles. So the same thing, the same observations I have here applied to triangles as well, right? So we counted them just by saying a set of 3 adjacent vertices. So we counted this as like 1 triangle, not as 6 triangles. So that's a good point that, that wouldn't really jive with the way we counted triangles, right? Exactly, yeah. Then that's when things really start getting confusing, is even if I have just that, actually if I have the 1 edge, maybe it's fine. But if I have the 2 edges, then if I could think, okay, maybe I have 1 copy here because it's 4 vertices that have a 4 cycle, but you could also think this is really kind of 3 copies because, you have like this one, you have this one, you have this one. Or if you wanted to really count all the different ways of labeling, then you could count actually 24 copies or something. But anyway, so all I'm trying to say here is it's a bit ambiguous what I mean by a copy. So we need to make that clear. And actually the way it's going to be convenient to count copies is actually none of these ways that I've described here. So for the purposes of this lecture, we're going to count copies in like a way of kind of measuring how many copies there are of a graph in another graph is going to be done in terms of counting homomorphisms. So this is bringing back to this question in the poll. So let's define what we mean by homomorphism. So a homomorphism from a graph H to a graph G, it's a function f. So actually, if you guys know, so it's from the vertices of H to the vertices of G. If you guys know isomorphisms, that'll kind of help here, right? And also if you know things like group theory, where you've seen the word, you may have seen the word homomorphism and isomorphism, right? This is the kind of natural kind of homomorphism of graphs in the sense that it's a function from the vertex set of H to the vertex set of G, which kind of preserves adjacency in the same way that a group homomorphism preserves the group operation. So it has the proper, so such that if UV is an edge of H, then F of U, F of V is an edge of G. Yeah, so that's exactly right. So, and so I don't know how many people do know about group theory or not, or yeah, I don't know what kind of parallels to draw here, but it's kind of, it's also, so if you do know about groups or fields, or I mean, what other things have homomorphisms and isomorphisms? Lots of things, I guess. But yeah, in groups, for example, when you take a homomorphism, the idea is that it preserves the operation and it becomes an isomorphism if it's also a bijection. This homomorphism, so there's something a bit careful, you have to be careful. So let me, actually maybe I'll, in red here, maybe I'll write what would make it an isomorphism. So it's an isomorphism. So you need, to make it an isomorphism, it has to be bijective on the, it could fail to be surjective, injective, or both, this homomorphism. So it's an isomorphism if it is bijective, but it has to be bijective not just on the vertices, but also on the edges, if that makes sense. So it's bijective on the vertices, and it's a little bit awkward to say this, that it's bijective on the edges. But if you think about a homomorphism, like, so it's formally, it's only defined as a function on the vertices, but it does induce a function on the edges, because if you think of an edge, you can think of like f of the edge uv as being the edge fu, f, f of u, f of v. If you anyway, let's not worry too much about that. And another way to say an isomorphism is to say it's bijective, and actually instead of a one direction here, you have an if and only if it's a bijection. But I'll erase that just to, but anyway, so the point is a homomorphism, so we don't really need isomorphisms, but a homomorphism is something that preserves adjacency. Let me kind of put that off here. And then I'm going to define a number, hom hg, to be the number of homomorphisms of H to G. And in some sense, you can think of this hom hg as being a way of measuring how many copies of H there are in G, right? Although it's because of this fact that homomorphisms don't have to be even injective, it's not what you would usually think of as a copy, because you can map, if you have certainly if I have a copy of H in G, then that's going to contribute, like if I have literally just, if you look inside of G and you see a subgraph which is isomorphic to H or something, that's going to give me a homomorphism, right? So kind of the homomorphisms do count all the copies in the way that you would normally think of copies, but they also count some other stuff, right? Because it might not be injective. So it's kind of like a copy of H where you map two vertices to the same vertex. But in some sense, if we kind of expand our definition of copy, then you can think of this as counting copies. Does that make sense? I understand it's a little bit weird, but it's going to be a really convenient definition for what we're going to prove. It might be something like that. We're going to count it in a second, but I think it's actually even bigger than that. I think it's yeah, I think it's bigger than that. But we'll think about that in a second. Actually, that's a good example to think about. So let's so we will do that one. So a triangle actually wouldn't, weirdly enough, a triangle wouldn't count as a 4-cycle because basically what will I mean, when you think about a homomorphism of a 4-cycle into a graph, I mean, it could map injectively, and then it just looks like a 4-cycle. If it doesn't map injectively, then so in other words, if two vertices map to the same vertex, then it has to be two non-adjacent vertices because G doesn't have any loops. So a kind of copy of C4 might look like an actual C4, or it might look like this, right? Or it might be like an edge where both pairs of non-adjacent vertices get collapsed. Okay, I understand this is a little bit weird, but does that help for the question about triangles? So I think, yeah, you can't really collapse in a homomorphism. You can't really collapse. If you could map those two to the same vertex, then it would give me a triangle. But I can't map them to the same vertex because it wouldn't be a homomorphism unless G had some loops. But we don't think about loops in this course. Okay, right. So as was kind of anticipated by the question before, let's actually count homomorphisms of C4 into C4. Okay. So what is this home C4 C4? Now, yeah, you can kind of think of this sequentially. So how many ways can I choose the image of 1? So how many ways can I choose, so choices for f of 1, and like without thinking about any of the other vertices, right? And now by symmetry, it's not hard to see how many choices I have for f of 2, let's say, right? So 1 maps somewhere, and yeah, but kind of by symmetry or by the fact that every vertex has degree 2, right? So yeah, so 1 is going to map somewhere in here. It might map to itself. It might map somewhere else. Every vertex has degree 2, so there's going to be 2 choices for f of 2, meaning, and when I say choices, like of course, overall there's 4 choices, but what I mean is, so this is choices given the choice of f1. So once f1 is already chosen, because so suppose I map 1 to 3, if 1 goes here, then basically 2 needs to be one of the neighbors, so it has these 2 choices. And similarly, the number of choices for f of 3 is also 2. And if you think about it, so this is, again, given the choice of f of 1 and f of 2, but the choice of f of 2 didn't really affect f of 3. So it would force f of 3 and f of 4 if we had to be injective, but it's perfectly allowed to say put 1 to 1, put 2 and 3 here, and put, say, 4 here. That would be perfectly allowed. But yeah, so that's all. That's this injective thing again, right? So, and then if you think about it, no matter how you place everything before it, you actually have again 2 choices for f of 2 or f of 4. So that might be a little bit hard to see, but if you think about it, if I chose 1 to go to 1 without loss of generality, suppose I chose 2 and 3 to both go here, then f of 4 has to be a neighbor of f of 2 and f of 3, which is, the choices are either 4 or 1. If, on the other hand, maybe I chose f of 1 to go here, f of 2 to go here, and f of 3 to go here, but again, I have the choices 4 or 1 for f of 4. So I think that gives you 32 choices overall. Okay, yeah. Yeah, it's easy to kind of count these things in the wrong way or something and just miss a few. But yeah, if you think of it sequentially like this, it works pretty well. Are there any questions about that? I know that's all of this is a little bit weird. Yeah, so this is what I just computed. Okay, now building on top of this a little bit more, we're going to define something called the homomorphism density of a graph H and a graph G, which is just, so the notation is THG. I have no idea why people chose T for the letter here. I mean, it seems like D or something would make sense, although maybe D was already taken. I mean, in graph theory, D gets used too often, right? Degree, distance, etc. So maybe, yeah, T was the choice here. So it's the number of home HG, remember that's the number of homomorphisms from H to G, right? Number of homomorphisms, homes from H to G. divided by v of g to the v of h. Okay, and where does this v of g to the v of h come from? Well, that's just the number of functions, like total number of functions from the vertex set of h to the vertex set of g. So that's counting. So the top thing is counting the homomorphisms, and the bottom thing is counting all the functions from vertex set of h to vertex set of g. And remember, a homomorphism is one of those functions, right? Like a homomorphism is a function from v of g, h to v of g, which has a certain special property. So intuitively, not even just intuitively, but this is the definition, that, in other words, this THG is like the percentage of functions from v of h to v of g that happen to be homomorphisms, right? It's just count all the homomorphisms and divide by the number of functions. So it's like the proportion of functions which are homomorphisms. Or in other words, suppose I took a function from v of h to v of g randomly, or like put them in a bag and pick one out of a hat, or pick one out of the bag. I don't know how they got in a hat if they were in the bag, but put them in a bag and pick one out at random. This would be the probability that it's a homomorphism. So this is so far just a definition, but is it clear? Okay. Maybe, I'm not sure if I have time for this or not, but let's just do it anyway. So here's a poll. So so I've got a graph with n vertices and m edges. So then I've put a poll up with a bunch of expressions. Which of these expressions is correctly, which of them is equal to t k2 of g? So k2 is, of course, just like the graph with two vertices and one edge. So which of these things describes, so where here in the green, I've repeated the the formula for it. Yeah, I wouldn't say the whole course, but it's definitely going to keep coming back. But actually, yeah, this homomorphism density stuff is going to be used today, next time, and if things go according to plan, then like the very last lecture of the entire term. So yeah, this homomorphism density isn't like something that comes up all the time. Although actually everything we did last time could have been phrased in terms of homomorphism density as well. I just didn't want to define it yet. Okay, so we're getting some answers coming in the poll. All of them are kind of in the right direction. Not all of them are right, but I think there's, a lot of them just have one piece missing, I guess. So yeah, so what's the denominator? This one's easy, I think. When I'm dealing with K2. So yeah, exactly. So the denominator is just n squared. It's n number of vertices of G to the number of vertices of H. H is K2, so it's n squared. The numerator, so there's a lot of people picking things like M, which feels natural. It's the number of edges, but actually it should be 2m, because if you think about it, every edge of G, like if I look at an edge, there's two different homomorphisms that map to that edge, this way or that way. Right? So there's two ways to map to that edge, either this way or that way. And of course, if I take a function from the K2 to G, which doesn't map to an edge, then it's not a homomorphism. So like there's a one-to-one correspondence between like directed edges of G, like take an edge of G and orient it this way or that way, and homomorphisms. So yeah, it's 2m. So the answer ends up being 2m over n squared. So that's good to keep in mind, because actually that's going to be needed in the proof coming up. Okay, so here's what we're going to prove. That for every graph G, so the homomorphism density of C4 in G is always at least the homomorphism density of an edge of K2 raised to the fourth power. Not sure if that seems natural or not. Probably not. But we're going to also, if we have time, we'll also talk about some tight examples and stuff. But yeah, so this is, by the way, this is the thing we just computed in the poll, right? This is just 2 times the number of edges over number of vertices squared. By the way, that's also the quantity we were dealing with in the last lecture, 2 times number of edges over number of vertices squared. So in other words, if the number of edges in G is something like alpha, so this is connecting to last time, kind of. if the number of edges is alpha n squared over 2, then the number of homomorphisms of C4 into G will be at least alpha to the 4 n to the 4. That's actually equivalent to what we've written here. Right. And then that kind of gives you an idea of how many copies of C4 G has, right? Okay, it's not copies, it's homomorphisms. But homomorphisms, like I'm saying, it's kind of like counting copies. So this is like a supersaturation result for C4. If you have way more than the extremal number, then the number of C4s you should expect is something like, at least, like the edge density to the 4 times n to the 4, if what you're counting is homomorphisms, not actual C4. Okay, maybe that was just confusing, but let's prove this theorem. So first what we're going to look at is actually a different graph. So we're going to look at paths on 3 vertices. Yeah, so if we counted injective homomorphisms, we would get actual C4s. That's right. And actually, if you think about it, if the number of homomorphisms is like bigger than n cubed or something, then you have to have some injective ones. But let's not maybe think about that too much. So yeah, if you have alpha to the 4, n to the 4 homomorphisms, then most of those ones are actually injective. And that's kind of how this translates into counting copies. Okay, so let's look at how many homomorphisms from P3 into G are there. So where P3 is this graph, path with 3 vertices. So there's, I mean, various different ways you could try to count that. Sorry, was that n times 4? I think I've got a lot more options because, well, oh, sorry, this is, so maybe, yeah, you're thinking into C4 here, aren't you? So I'm actually counting it into G, but actually your observation here is kind of, I mean, it's correct and it generalizes to any graph G, right? So what would you do in a general graph? So I'm going to write it as a sum, but picking the central one is what I want you to do. So if I pick the center one to be V for some V, then the number of ways to choose the first, where 1 goes and where 3 goes, well, it's going to be dV squared, because I just pick 1 to be any neighbor of V, and I pick 3 to be any neighbor of V. And now we've got our favorite inequality that seems to come back every class. Can anyone tell me what to write in any of these three blobs? In the green, the pink, or the blue? So there's okay. That's what I wanted here. Yep. So there's a suggestion of d of v plus d of u. That's one of the things that kept coming up. That's in Mantle's theorem and in Goodman's theorem, but unfortunately that's not the one we want here. But yeah, here I want, yeah, so sum of the degrees. What do I want in the blue? I guess that's maybe easy to guess, but yeah, the 2. And then the denominator is like the number of terms in the sum, which is, so I don't know if I'm dealing with n or with v of g, but let's write v of g. That's again this convexity thing. And this is just 4 times the number of edges squared because of handshaking, right? I get 2 eg inside of the square over v of g. Okay, so I've counted P3s. I don't know why, but I've counted P3s. So now let's turn those P3s into C4s. So what if I write down, I mean, how can I make this natural? So the way I wrote the number of P3s there, right, I could have also written it like this. So, following the suggestion, I chose the center vertex first, and then I chose the other 2, and that was the sum of the degrees squared. I could also choose the other 2 first, and then choose the center after that. So I could look at all the ways of choosing the first 2 vertices, or sorry, these 2, the endpoints. And after I've chosen those, I can get a homomorphism by picking, so actually maybe I should make this more clear, that this is actually pairs in the square of the vertex set. And if I pick this, I look at this, how many common neighbors they have, that's also going to be a way to count P3s, or homomorphisms of P3. So I guess I'm now kind of wondering what happens if I choose a pair of vertices and I choose 2 things. Well, I take the square of their common neighborhood. So it's kind of like choosing 2 things with replacement from their common neighborhood. And if you think about it, I pick 2 vertices, u and v. I pick something that they're both adjacent to. I pick another thing that they're both adjacent to. I allow these to be the same thing if I want. I don't really care. I could pick the same thing twice. I could also pick the same first vertex twice. But yeah, if you think about it, this is actually equal to the number of homomorphisms of C4 into G. So the fact that I've got this thing where you don't have a square and this thing where you do have a square means that I can actually apply this convexity trick again. So, okay, so what we wrote on the previous slide is that the number of homomorphisms of C4 into G is what I get when I take two pair of vertices, look at, choose two things from their common neighborhood, and I just do my whatever Cauchy-Schwarz or whatever you want to call it, or convexity thing. And so it's on the back of my slide, or my video here, but yeah, squared over, okay, so here's the question, I guess. What is the denominator here? So the thing in my video, actually, I kind of want to divide both sides by this n here, if that makes sense. That's what I'm really applying in these things. But yeah, you have to be careful because the n here in my back of my video, that comes from the number of terms in the sum. The number of terms in this sum is not the number of vertices, right? It's the number of vertices squared. So the thing that you put on the denominator in this kind of inequality is the number of terms in the sum, right? And this sum goes over all pairs of vertices. And then I wanted to say that this is equal to homomorphisms of P3 into G squared over vertices squared. Because the thing inside the sum here, like on the previous slide, we came up with a formula for that, which is just homomorphisms of P3 into G, right? Because if I pick two vertices and pick a common neighbor, that's what a homomorphism of P3 is. So we're kind of applying this convexity thing twice. Is it clear? Are any questions? Yeah. So yeah, it'll also have pictures like this, and also these two vertices could be adjacent or not. I have no idea, but basically, yeah, it'll count homomorphisms because it kind of counts like ways of picking, say, U and V as being two specific, like vertex 1 and vertex 3 on the C4, and then it says how many ways can I pick vertex 2 and vertex 4 if I think of it labeled 1, 2, 3, 4 like this. But yeah, anyway, there could be an edge between the vertices I choose as 1 and 3 or not, or whatever. Yeah. Okay, so just kind of wrapping this proof up, then we've got these kind of two inequalities that we've proved. So we proved that, this thing is at least this. So now I've switched to saying n is the number of vertices for some reason. And we proved the lower bound also on this this home P3 of G, which was like this. So that was like 2 slides ago. So this is at least this, which is at least this. And you do all the algebra, and then what you end up with is 16 times number of edges to the 4, because so the 4 becomes squared, edges squared becomes squared, so it's edges to the 4. You get n squared on the denominator, which combines with the other n squared to make n to the 4. And then if you just use so this is what we derived when we were doing the poll, that the density of K2 in a graph is 2 times the number of edges over the number of vertices squared. So basically, if you do maybe if you write E of G in terms of, TK2 of G, and then you substitute, you actually get that this is exactly equal to this lower bound that we wanted. It's exactly equal to TK2 of G to the 4, n to the 4. Finally, you just divide both sides by n to the 4, because, yeah, TC4 of G, right, is the number of homomorphisms into G divided by n to the 4. So when I divide both sides by n to the 4, the left-hand side, so this is the left-hand side, it's way over here. That's the right-hand side. Yeah, the left-hand side just becomes the density of C4 in G. The right-hand side becomes density of K2 raised to the 4th power. And that finishes things off. Any questions about that? I think, yeah, you should, by now, I guess, be starting to getting used to this, whatever it is, this sum of squares kind of lemma. Okay. Yeah, natural question then is is this thing tight, right? Is there a graph which has, TK or C4 of G roughly equal to, or even equal to TK2 of G to the 4th power? And the examples we get come from random graphs. So let G be a graph on n vertices, where for each pair, for each pair of vertices, we put the edge UV into G with probability P, independently of all the other edges. So in other words, And I think we've kind of looked at, or maybe I don't know if we looked at random graphs specifically, but for each edge, I just flip a coin with probability P. I put the edge there. So with probability P, with probability 1 minus P, I put a non-edge. If P is a half, then it's the nicest case where you just flip a coin, and with probability a half, you put an edge. With probability a half, you don't put an edge. So, and this is, kind of a question for you. So what's the average value, like what's the expected value or average of the number of edges in G if G is constructed in this way? Yeah, exactly. So the average value of this thing is going to be P n choose 2. Again, you can do this by like linearity of expectation or something. Every edge has a probability P of coming into the graph. So by linearity of expectation or something, you have Pn choose 2 edges on average. And that means that the average value of this edge density, so tk2 of G is just 2 times the number of edges over n squared. So that's going to be roughly, so remember, n choose 2 is roughly n squared over 2. So roughly the tk2 of G is going to be P. So that's not exact, but that's approximate because of the fact that n choose 2 is roughly n squared over 2. So kind of, this thing kind of almost cancels with this thing. And what would you expect for C4 of G? Well, if you look at any function, like, okay, if it's a function, as long as it doesn't map, I mean, how to explain this? For example, think of an injective function of C4 in vertices of C4 into G. If you took an injective function with probability, so I take 1, 2, 3, 4, and I want to say what's the probability that this is a homomorphism. This edge is present with probability P, that edge is present with probability P, and that one and that one. So the probability that you see a homomorphism here is kind of like P to the 4. So every homomorphism or every mapping is a homomorphism with probability P to the 4. So we're going to get, yeah, exactly. So we're going to get roughly P to the 4 here. Of course, here I kind of was thinking about them being injective, but if n is very large, imagine you have, you take the number of people on the earth, which is billions, right? I pick 4 of them, or I pick 4 people with replacement. So I just pick a random person, put them back, so I'm allowed to pick them again. I pick another random person. I do that 4 times. The chances of getting the same person twice is basically 0. So, right. So basically, as n gets larger, pretty much every function is injective. So roughly, you do have 4-cycle density P to the 4. All of these things are asymptotic as n goes to infinity. But yeah, so basically, this lower bound is tight, at least in the limit as n goes to infinity. So maybe we're kind of out of time here, but just wanted to quickly mention this theorem or this conjecture, which is a famous open problem called Sidorenko's conjecture, which would generalize this result, right? So it says that if you have any bipartite graph, then for every graph G, the homomorphism density of H and G is at least the density of K2 in G raised to the power, which is the number of edges in H, which if H is C4, right, then that just gives me a power of 4 here, right? So this is an unknown conjecture, but very natural and very kind of famous.